Hi, this is Shelley Physics, episode on applying Newton's second law. Today we're particularly talking about statics, as there are situations where the acceleration of an object is zero or the forces are balanced as acting on a body. So we'll look at like structures and holding up weight and things like that. All right, so when I like to call this one problem solving boot camp level 2, where level 1 was problem solving motion problems. Level 2, this one we're involving some diagrams. We're going to involve force diagrams in this one because we're going to first analyze a scenario, look at what's happening in that scenario, think about the forces acting on the object at hand, and that force diagram is going to be the key centerpiece to starting out our problem solving process. Throughout this episode, we're going to be looking back at this problem solving text here. This is a process and this is something to practice. You'll have this out as you start embarking on trying to do the first couple of problems here. And after you get through 4 or 5, you'll start to be familiar with it. After you practice it more and more and do the same kind of process over and over again, let's say after 12 or so problems, you're going to feel very comfortable with it. And finally, we're going to keep on adding on little aspects here and there, like what about friction? What about weight? What about centripetal forces? As we go through this unit, we'll just be adding on small pieces, but every single time we're going to be revisiting this problem solving process. So I can tell you how many times I've taught this course where students have been resistant to this, and they're the ones that really struggle. Those that go all in and try and say, okay, I'll try it out your way, and they'll become really familiar with it, and they're the ones that tend to succeed much better. There are multiple ways to solve problems given, but this one helps you get through all the time. Even if you have no idea how to get from the beginning to the end, this is a stepping stone, this is a guide, call it a map. It'll help get you there. So our first step is when we're looking at a scenario, we're going to be drawing a force diagram, labeling those vectors, like in the force vector activity, force vector video. If we know a value of a force, we'll label that value. Number 2, I'm going to come back to this, but sometimes it's going to be important to look at a scenario sort of differently. Instead of looking at things like straight up and down as y is the up direction, it may be helpful, let's say on a ramp, to look at the direction that's perpendicular to the ramp as the y direction and side to side parallel to the ramp as the x. Number 3, we're going to take any angled forces once we've done that, and once we've determined our orientation, look at any angled forces and break them up into their x and y components. So we're going to be resolving forces into the components, and that will give us a nice, neat force diagram with all the forces in the y or the x directions. And we'll be ready to apply Newton's second law. So we're also going to look at how to sum the forces, set them equal to ma in both the x and y directions. And those will give us a system of equations that we can use every single time to come out with our result. Number 5 is solve the system of equations, and finally consider does the solution make sense. So this is the process I'm going to bring up over and over again as we go through. All right, so first we'll take a sort of simple scenario. Let's take a hanging sign. We own a fruit stand and we want to sell watermelons. So we got a hanging sign here. Now I'm not going to label it watermelons, but this is what we do to start out with a force diagram. And we think about this hanging sign. It's got 2 cables on it. Okay, maybe a little picture. Here's our stand. There's the storefront. There's the door, and we might have, you know, a stand of watermelons sitting in the stand. There we go. And we want to hang a sign above it that reads watermelon. So there's 2 cables. They're evenly spaced. This sign has a mass of, we'll call it 5 kilograms. It's a heavy sign. And engineering wise, we want to make sure that this heavy sign, it's heavy because we don't want to blow around in the wind. We want it to hang down. We want to attract a lot of attention, so it's going to be a large sign. So as we're store owners, we want to make sure this doesn't fall and hit people in their heads. So we need to hang it with a strong enough cable such that it won't be blown off or blown around in the wind and snap the cables. So we'll have a couple of cables spaced evenly. And they're each going to have a tension force. So I'm going to label these with a capital T. Now you could do a F capital T as a subscript. But being evenly spaced, these would have the same amount of tension force. They're supporting about the same amount of weight on this sign. And what else? It's got a mass. So mass is attracted toward the center of the Earth. So it also has weight. We got an Fg in here. Now, if you think about it just conceptually, you don't have to know this ahead of time. But since this sign is something that we want to stand at rest, it's going to be in equilibrium. That means that the weight of the sign has to be balanced by the two tension forces holding up. Each of these cables is going to share the weight. Share the load, Mr. Frodo. They're going to share the weight of the sign. So this weight force should be larger than the tensions. All right, what I've just done here is I've labeled my force vectors. I'm drawing a force diagram. Let's flash up that problem-solving text. There it is. So I drew the force diagram. I'm labeling the forces with vector arrows with all the known forces and unknown. So tension is unknown at this point. There are no angles involved. There's no angled forces, so I don't have to worry about that yet. And it says provide values for all knowns and identify target variables. Okay, so that's an important thing to do here. My question is, what is the tension in each cable? So I've identified the target variable. This has a tension T and this also has a tension T. We're going to look at scenarios later in this lesson where the tensions may be different because they're going off in different directions. Okay, but in this case we're assuming that they're holding the same amount of weight. So they should have the same force. But that gets us to weight. Do we know what the weight is? Actually, we can figure it out. Force due to gravity is mass times acceleration due to gravity. So this is always on Earth, mass times 9.8. And if you memorize anything in this course, this is one of those things to memorize. If you're given a mass, you can determine the weight force by multiplying the mass times 9.8. And that would give us 49 newtons. Okay, so that's labeling a known force value. All right, so let's go back to the problem-solving text. I think we're done with step one here. Number two, let's just consider, is this a good orientation? Is up and down good for the y direction? I think it is. We don't have anything on slopes and there's no angled forces, so let's keep it simple. It looks good to me. Number three, are there any forces at different angles to resolve? No, so we're going to come back to that step later also. We're actually on to number four because we have all the forces in the y direction. If we had them as long as we have them all in the x direction and the y direction, we're ready to go on with step four. Is apply Newton's second law in both directions. X doesn't apply here. And substitute expressions. Okay, we've already kind of did a substitution here with a known amount. Now, if we didn't know the mass, step four would also include substituting like an mg for every force due to gravity. But we're ready to move on to step four. Let's apply Newton's second law. So I'm going to demonstrate that right now. Newton's second law says the sum of all the forces acting on a body equals mass times mass of the body times the acceleration. Now, right now we're simply looking at the y direction. So I'm going to label this with a y force, and this will give us a y direction acceleration. Now, the y direction acceleration is the only acceleration possible in this scenario, unless somebody comes by and smacks the sign on the side, like I know one of my sons would probably do, maybe both of them, and that sign would go swinging back and forth. Then there would be no x direction acceleration, but everything's possible in the y direction because of gravity here. So as we sum forces, refer back to force diagrams lesson if you need help with this. But I've got two tensions upward. I'm going to call up as the positive direction. Really doesn't matter in this scenario, but I'm going to take up as positive. So we got a tension pulling the sign up plus another tension pulling the sign up. Now as a sum, I'm going to be very technical here. I'm going to add a negative 49 newtons. If you didn't know the mass, you might have a minus mg here. But you don't have to do plus a negative 49. You don't have to do plus a negative every single time. You can just write out minus 49 if that makes sense to you. But I just want to show you that this is a sum. The weight is just working against the two tensions. So they're going to take away from one another. And this equals mass times acceleration. The mass is 5. And the acceleration is in the y direction. Now I'm going to drop the subscript here because I'm just going forward with the fact that there are no x direction forces. So I'm just going to leave this as the overall A, the acceleration. All right, let's consider what's going on here. What's the tensions? On the left side, all this is the sum of the forces. So equation-wise, that's what the sum of means. We're going to add them up. We're going to consider every force in the y direction. Okay. Now I can simplify this a little bit. T plus T is 2T. I've got a minus 49. Now over here, I don't have the acceleration, or do I? As a store owner, I do not want my signs accelerating off their cables. So that's the other assumption here. To figure out T, the acceleration is 0. We don't want these to move. They're at rest. They're constantly at rest. The constant velocity is 0. So with a constant velocity, we have 0 change in velocity or 0 acceleration. So the acceleration is 0. Once you get to a scenario like, oh, I don't know what to do there, take a moment. When you get stuck, don't stop. Keep moving. Like, well, what is A? It's at rest. That's right. So plug in 0 for an acceleration. And now we have 2T minus 49 equals 0. So so all that is 0 there. If I add 49 to both sides, look what comes out here. We get a 2T, 2 times tension equals 49 newtons, the entire weight of the sign. And look at this. Even if you didn't have an intuitive feeling about how to solve this problem, Newton's second law will never fail you because it's a law. It always works. And look what it's telling you now. Each tension is exactly half the weight of the sign. So you might have figured that in the beginning on, Mr. Schellenberg, why are we going through all this? Can't I just do it faster? Yes, you can do it faster, but you can't always do these fast. They won't always make sense. They won't always be so obvious if you think this one is obvious. All right, so the overall tension is a 24.5 newtons in each cable. Okay, so they each hold half that weight. And it's the math is telling us here, Newton's second law revealed that the tension is exactly half the weight. So that weight gets split in half by each of those cables. All right, let's move on to another scenario. Something similar. Let's take a hanging sign now. Okay, let's do this. Have you ever seen an awning? An awning is sort of a stiff covering. We'll just call it a bar. And they're often held up by a cable attached to the building from the top. Okay, so here's an awning. And it's going to hold up another sign. Now, instead of having 2 cables, let's just make this kind of simple and straightforward. Let's say there's a hanging mass here. Let's also call it 5 kilograms as well. So that's our sign now. All right, so this is the side of the building. Our business has done so well that we're expanding to use the side street. And we had to put an awning over our fruit and our vegetables. So over here, this is a carrot sign. We're selling carrots over here, I guess. Okay. Now I need to tell a little bit about this cable here. It's at an angle of 30 degrees. And you see in this scenario, everything's kind of focusing right here. We got the weight pulling down, we got this tension attached there, and also this awning, it does serve a very important purpose. Those of you who have ever played football or sport where you had to reach out and touch somebody, okay? Have you ever heard of a stiff arm? That's kind of what the arm does. We've got this arm sticking out here, and it's keeping that matter outwards. It's keeping it from falling in. If this awning were to break, then this whole area would swing down and smash against the wall. Okay, so this awning here is pushing outward, while the tension pulls inward. It's a tension. It's coming back from a tension spring. A tension spring is one that can be stretched outward, where a compression spring is a spring that can be pushed inward. So with that kind of thought, this is like a compressed beam. The system's trying to pull it inward toward the wall, while the beam is stiff arming it outward, is holding it out. So we call it a C for compression, and we can call this T for tension. And those give us a couple of unknown forces. So I'm going to back it up here to get our scenario back. And now I'm going to draw my first force diagram. So this is not actually necessary as a step. But my force diagram, I'm going to use as that central point of focus. Okay, this point right here. There is weight pulling down on that point. There's a tension pulling up this way. I can give that a little reference here. So I can put my angle in and label it T for tension. And then there's this bar. The bar doesn't pull in, it is keeping it out. Remember that. It's keeping it out that way. So there's an outward compression force. Call it C. And this is my first force diagram. My first step, I'm going to bring that up here in a second. Remind you to label all known forces. So again, here we would take 5 kilograms times 9.8 gives us that same 49 newtons. Let's keep it simple and allow us to compare. But we're not sure about the tension or the compression force. So let's solve for those. What is T going to be? Make it look like a T. And what is the compression force required by that beam, by that awning? Okay, so if this were an accordion or a spring, it might get squished backwards. But this is a stiff beam holding it out. All right, so let's take a look at the problem-solving text, problem-solving process. We drew the force diagram, labeled the vector arrows with all the known and unknown forces and angles. We have that involved now. Provided values for everything I know and the targets. I've got it up there. Number 2, is there an orientation? Well, I've got the weight pulling down and this compression going out. Those are in the X and the Y directions. Let's leave it. Okay, we don't need to look at this any differently. I'm probably going to come back to that step when we get into dynamics, when things are actually moving. But I'm going to try out one more here before the end that may involve changing the orientation. Number 3, resolve all angle forces into X and Y components. We're going to have to do something with this now. Draw a new force diagram to reflect only those vertical and horizontal forces. All right. So turn that back off. It says draw a new force diagram. So we're going to leave the Y direction force of 49 newtons and label that X direction force as the compression. That is not a classy arrow. That was a wibble wop. Oh, I just can't do it. This side-to-side motion is killing me. Okay, there we go. There's our C. But this T, this is an angled force. It has 2 components. It's got an upward component, it pulls up, but also to the right. So there's a right-hand component. Now again, this upward component, if you watch the force diagrams video, just translate that with your eyeball. It creates the side of a right triangle. Horizontal and vertical are exactly perpendicular to one another. So this is the opposite side of a triangle. So if we were to label those components, there's an up component to this. It's actually going to be, I want to size it the same as this one. We'll see why in a moment. And a right-hand component. There they are. But what are their values going to be? Well, down here, this is the angle is adjacent to the horizontal component. I don't want to get too much black out there because we want to keep that original, preserve the original diagram. But this lower part, this horizontal component is adjacent to the 30 degrees. So that's going to be the cosine component. Drawing out the triangle, we got a T, we got an adjacent side, I'll call it A, and we've got the opposite side, I'll call it O, with the curly. And we have the 30 degrees. So if we want to know A, cosine of theta is adjacent divided by hypotenuse. And if we multiply both sides by the hypotenuse, we're going to see that t's cancel, and the adjacent side is equal to t cosine theta. So this side to the right is going to be t, we don't know the t, cosine of 30 degrees. All right, that's important to know. T cosine 30, we don't know the t yet. Don't spend too much time thinking. Don't use the brain juice thinking about this one. It's just the sine component. This is the opposite side. So before you do too much thinking, that opposite side, this vertical component of t will be t sine 30. All right, and that's it. So I always, when I'm looking at these, I go, oh, which side is touching the angle? That's the adjacent side, that's the cosine. The opposite one is always the sine. Okay? So what have I done now? Shirley, what'd you do? I have completed step 3. I resolved the angled forces in X and Y components. I drew a new force diagram to show only vertical and horizontal forces. Now we're ready to go on to step 4, apply Newton's second law in the X and Y direction. Okay, I'm going to start out with the X. Sum of the forces in the X direction equal MA in the X direction. All right, so in the X direction, we've got, I'm going to call right is positive and up is positive when we get to the Y. So if right is positive, I got a 2 cosine of 30 degrees going to the right, and C going to the left. So there's a force called C, the compression force working against that. I'm going to subtract it. Same as plus as adding a negative C. There's a mass of 5, but what's the acceleration again? I don't want my sign to go anywhere. I want all my forces to equal 0 if we sum them up. All the sum of the forces equals 0. That means the acceleration in both directions should be 0. In other words, conceptually, look at the chart over here. What that means is our t cos 30 should equal C, and our t sine 30 should equal 49. That's what that whole equilibrium piece means. But applying it to the equation will never lie because it's a law. 5 times 0 is 0. Acceleration is 0. So I get a t cos 30 degrees, add C to the other side, will equal C. Mr. Shelley, I can't solve this. Well, when you get stuck, don't stop. Okay, just keep going. That's one equation of motion in our system of equations we're going to be able to solve. So let's not stop and start on the sum of the forces in the Y direction. Write it out. Just get used to doing this. Don't take any shortcuts here, because when the problems get more complicated later on, you want to have this method down. You want to be ready for it. You want to be trained. My analogy for this has always been to my students, it's like boot camp in the Army. When someone yells, "Hit the deck," do you stand up and go, what's going on? No. You hit the deck because something dangerous is about to explode, or you're going to come under enemy fire. So when someone in your troop who you trust says, "Hit the deck," you get down. That's the process. Then you look for cover. Then you get directions from your commanding officer. There's a rule set that goes through your brain when you're trained by boot camp, and it saves your life and it helps you win the battle. Okay? So that's what you're trying to do here. Save your life and win the battle. That's what problem solving becomes sometimes on those more complicated ones. So please practice this step. I'll probably reference a great scene from Forrest Gump where he's putting together his gun and Bubba's just talking to him next to him. But he's going through those steps. He's done it so often it becomes automatic. That's the place you want to get to in this problem solving. So please practice these steps. Write each step down. And I promise you it is going to be good for your health, your physics health in the future. So our Y direction, we're only looking at these Y direction forces now. And get rid of my scribble. So in the Y direction, we've got t sine 30 going up. See the theme here of projectiles and forces? Separated everything in the horizontal and vertical. I like to make it familiar. Minus 49 going down equals 5 times 0 acceleration. Okay, so we get a t sine 30 equals, we add 49 to both sides, equals 49. So look, we have a system of equations. If there are 2 equations and 2 unknowns, you can take the one and plug into the other. But look, we can actually solve this one right now. T divided by sine 30. I'm going to just write this out again. Sine of 30 is 1/2 of 0.5 in decimal form. And divide both sides by 1/2 is the same as multiplying by 2. I'm going off the screen here. Let me give us some more room. Okay, so that would be T equals 49 divided by 1/2 is 98 newtons. So I have one of my targets, and I'm ready to plug that in right up here to get my other target, to get C. So C is 98 cosine 30. I'm plugging in t, 98. All right, I calculate that as quickly as possible. 98 cosine 30. Feel free to make computer sounds, cheesy 1950s and 60s computer sounds while you're calculating. Good. And we got 84.87. Looks like I'm doing 2 sig figs in this problem, so I'm just going to say 85 newtons is my C. And there it is. Okay. Now, before I mention looking at something with a different orientation, I might do that more in our dynamics view instead of statics, when things are moving and accelerating. But instead, I'm going to do one more. I've done the whole process, demonstrated everything. So if you just need one more example, I'm going to give it. This one will involve 2 different tensions at different angles. There's nothing past this problem, so if you're ready to get started with your own work, please feel free to do that and stop this video. But if you do need another example, if you get to harder problems, you might come back and check this out. So let's say we got that, let's mix it up. We got a 10 kilogram bowling ball. Oh, that's small. Come on, Shully. There we go. It's a 10, I keep on doing this little stem at the top. This is a 10 kilogram apple. It's a 22-pound apple. There you go. And we're suspending this apple for show. Just say, hey, look how awesome my apple growing skills are. And let's say there's a tension. I'll call this tension 2 over here at 20 degrees. And let's do a kind of a strange angle. Let's do tension 1 coming up this way at 75 degrees. And there's going to, of course, be a weight to this heavy apple. So I made up a scenario, or I read it from a word problem, whatever it is. I drew the force diagram for it. Next, can I figure out what weight is? Yes, weight is mass times 9.8. So this one is going to be 98 newtons is a weight. And the question is, my targets, what is T1 and T2? What is it going to work out to be? All right. What's our problem solving text tell us? Drew the force diagram. Okay, orientation. Everything seems to be up and down, left and right. We're not on a slope. So again, I'm going to get back to that on another episode, working with objects that do accelerate. But we're trying to hold this apple at rest. So I'm going to resolve all the angled forces into x and y components and apply Newton's second law. Okay, so let's do that. We're going to draw a new force diagram. There's the 10. It's got a weight of 98 newtons. All right. Now tension 1 pulls up and to the left. I may have drawn these force lengths a little wrong, but we'll find out. And tension 2 pulls up a little and to the right. Okay, do you see a little issue here with how I drew my initial force arrows? I don't think tension 2 is going to be as big as I drew it. All right, but because if the acceleration is 0 for our system, if I'm trying to hold this apple at rest, then the left-hand force should equal the right-hand force. Okay, but you don't always have to draw them perfectly. We're actually trying to figure out these values. So I'm going to keep it like this, just saying that there's a little bit that's unknown about these two tensions. Okay, but the overall, there's a component of tension 1 pulling up. There's a component of tension 2 pulling up. Tension 1 has an opponent, a component pulling to the left. Tension 1 pulls to the left. Tension 2 pulls to the right. So I'm also going to add those same kind of arrows over here. There's the upward component from those two tensions, and there's the outward components. I'm just going to redraw those now to how they should kind of look. So these two up arrows should equal about the length of the down arrow. The outward arrows, because we're in equilibrium here, should be equal and opposite. So what do we label these? On tension 1, the side that touches the angle is the horizontal piece. So that one's going to be labeled T1. The one touching is adjacent to the angle, and that's cosine. And the angle is 75 degrees. So T1 cos 75. That automatically makes this top component T1 sine 75. We'll see that again over here. The 20-degree angle is adjacent to the bottom, the horizontal component of T2. So that's going to be T2 cos 20 degrees. And the up component would be then the sine component, T2 sine 20 degrees. Whoop, there it is. I've got all my forces in the y direction and the x direction, so I'm ready to move on to step 4, apply Newton's second law. I'm going to start out with the x direction here. Doesn't matter which one. Usually I'm going to start out with the direction that has a number in it, like we know the 98, so I'd usually start out with that because I'd be able to solve for the unknowns. In this case though, I'm going to have a system of equations, 2 equations and 2 unknowns in each one. There we go. So write that out, get used to the process. To the right, I've got T2 cos 20. And to the left, in the opposite direction, I'm going to subtract T1 cos 75. That equals mass times 0 acceleration. Again, don't shortcut it here, get used to it, because in just a lesson or two, we're going to be working with non-zero acceleration. So get used to putting it in. It's very healthy. All right, I can simplify this a little bit. T2 cos 20, if I add T1 cos 75 to both sides, we're adding it to 0, so that'd be equal to T1 cos 75, and divides both sides by cos 20. And these are really weird trig numbers, so I'm going to go ahead and come up with a number, a value for them. So T2 equals T1 times, let's see, cos 75 divided by cos 20. There we go. Computer sounds. 0.275. I don't want to lose too many of my decimal points here. Since this is not my final answer, give us some more room here. I'm going to leave some of those decimals in there. So 0.2754. We keep it at that. All right. I'm a little stuck here. I don't know what T1 or T2 is, so I can't solve for either, but I'm not going to stop. We're going to go to the y direction. All right, let's glance back at our force diagram. We've got 2 forces going up. We've got T1 sine 75 plus, it's in the same direction, T2 sine 20 minus 98 newtons. So we're looking at just the vertical forces here. Equals mass times 0 acceleration. I get a little divider. I can simplify this a little bit. I'm going to bring the 98 over the other side and figure out these signs. I'm going to go ahead and save that step. So sine 75 is 0.966. Plus T2 sine 20 degrees, 0.342. And add 98 to 0 on the other side. There we go. So there's our 2 equations, our system of equations. I've already got this one set up for what T2 represents, so I'm going to just take this value and substitute it over here for T2. And that'll give us we're solving by substitution. That'll give us an equation with just T1 as the unknown. So I'll rewrite that. T1 times 0.966 plus T1 times 0.275 is what we're substituting in for T2. But don't forget to multiply by the 0.342 out here. That equals 98. See, by substitution, we have this value. Now, if you got 3x plus 5x, that equals 8x. You'd add those coefficients together. So likewise, I'm going to add the 0.966 to the product of these two. So 0.966 plus the product of 0.275 times 0.342. That's 1.06. So I got a 1.06 T1 equals 98. And give us enough room. Divide both sides by 1.06. A little less than 98. T1 is holding almost all the weight there. Do, 92.45. So I'm going to say 92.5 newtons. We have T1. I'm going to substitute that in up here for our system. So I'm just going to multiply that 92.5 times 0.275. And we get about 25.4. Oh dear, what is that? That's supposed to be a 2. T2 equals 25.4. Got a little dysgraphic there for a moment. All right, that's it. We solve for unknowns. That gives you a sense of what we're going to be doing for this entire unit right here. Okay, we're doing this over and over again, building on a few concepts here and there. But please come back to this video if you need it in the future. Look at the flow, practice this over and over again. That is going to do very, very well for you, and you're going to be an expert if you practice this method over and over again. There's really not much thinking to do. You don't need to know the answer in the beginning. You don't have to go, well, let me consider if blah, 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 blah. You just go and do it. It's a process. It's based on a law. It will always work for you. I hope this becomes helpful for you.